Hello, me again. If you remember in the last video we talked about these things called phase portraits, and we kind of started looking into them. Hopefully it's kind of settled in a little bit now. But this is basically what we ended up with. If you remember, we defined, well, first of all, we started off with a function, y, which is going to be a function of t. Okay, so yeah, we had y as a function of t. And then we said, well, if we differentiate that, I'm going to actually call that a different function. So I'm going to say that if we differentiate that, we're going to end up with f of y of t. But just convenience, I'm just going to call it y. So, yeah, and we formed an ODE from that, and then basically we considered the phase portrait in each cases. So, like for example, this is what our derivative. When derivative is positive, it basically means we're moving to the right. When our derivative is equal to 0, it basically means we stay where we are. So in these places, essentially, we're staying where we are. These are our equilibrium points, A, B, and C. And when it's negative, we're basically moving to the left. All right. Now, in this video, I want to kind of expand on that and just reinforce that idea a little bit more, and also then talk about this thing called stability. So I suppose I should really start with this, which I kind of glossed over deliberately because I didn't want to give you too much information. The thing is with this, let me just say this. ODEs are just, if you like, an extra dimension to what you've been considering before. Right, so if you like, you've got a complex, with complex numbers, let's say, with a complex number, you can plot that graphically. On this axis is all our real numbers, okay, and on this axis now is our imaginary numbers, all right? It's exactly kind of the same thing here, except here we've kind of got y, and we've sort of, if you like, we've combined y as a function of t, y and t. So normally we would draw y and t like this. Okay, so we'd actually put t here and y here. Yeah, this is what y is equal to y as a function of t. It's like, y equals f of x. Yeah, on this axis we would put x, and on this axis we would put y. Well, I'm using the same thing, except I'm just denoting this by y. The function is y, and the variable is t. The reason for that is otherwise we'd have all sorts of horrible notation, but you could argue, well, actually this is even more horrible. It'd just be very long if we put all the right stuff in, but this is conventional, so we might as well we have to stick with it. So this is how I would draw y is equal to y as a function of t. All right, and I draw t on this axis. This t is our independent variable, and y on this axis, which is our dependent variable. Well, then what I do with this case, like I was trying to show you with the complex numbers. See if you can work it out for yourself. With this case now, what I'm doing is I'm combining these two axes into one plane. All right, so I'm basically getting y as a function of t. So if you like, I'm just considering this axis. Okay, but I'm combining all the ideas which happen in this axis, in this coordinate plane, into one plane, which is this one down here. And then on this axis, I'm going to have f of y, which I've defined. F of y is going to be equal to dy by dt. Alright, so hopefully that makes a little bit more sense about what's happening now. And so, if you remember, when we finished off last time, we considered this situation, this first graph on the left here, and we considered some kind of graph, and then we considered actually what's happening. And so basically we came up with y. Now what I want to try and do is I want to now try and put this phase plane back into this y and t coordinates, and hopefully then we come full circle, start to sink in a little bit, have a think about it, about what it actually means. Alright, so basically I want to take this here, this y-axis, and I want to put it as a function of t. So what's going on here? So this is y, and I'm going to actually plot t here. Okay, so y and t. So I'm taking this, which is, if you like, this axis here. So I'm going to put A, B, and C somewhere. Well, I've got to work out where A, B, and C actually are. Well, A is going to be negative, isn't it? Because if you can see here, I'm just taking this axis now. All right. So you can see here that A is to the left of this axis, which means that y equals A is negative. So A will be plotted down here. B will be here. And C will be a little bit further up than A. So A, B, C. So this is how I'm going to plot it, like this. So A, B, and C. And this is 0, 0, 0. 0, 0. Alright, now what I'm going to actually do is I'm just going to put in a dotted line for C, and I'm just going to try and show you what's actually going on. And the same for B and the same for A. So let's just have a look and see what's actually going on. So remember I said let's look at this phase portrait now, and now I'm going to try to actually draw my solution. This is actually my solution which I'm drawing now. So I've taken my ODE and I've got that graph from my ODE, which I can draw quite easily. And then I've drawn my phase portrait, and from that phase portrait then I can basically get back to my solution. My solution is just my original graph, my original set of axes, Y and T. Does that make sense? Okay. So what's happening? Well, let's look at A. A is moving to the left of A. We're moving so to the left of A, we are moving towards A. So let's consider over here, as we move through time, time moves in this direction, okay? So Y is getting bigger, so it makes sense that as we move forward through time, Y is getting bigger, so we're moving to the right. As time gets bigger, we're going to denote that as T approaches to infinity, we move to the right. All right. Well, as time gets bigger, as we move along this line, notice that we get closer and closer to A. These arrows say that we're getting closer to A. So if we start down here on this y-axis, okay, as we move through time, so as we move kind of now, you've got to, this is what I mean. It's really simple if you get it in your head, but it's really confusing if you don't, and you're thinking, what on earth's going on? So as we move through time, we're going to start out at a value which is less than A, but as we move through time, we're going to become closer to A. This is what this is meaning. So in other words, I'll just draw it and hopefully you can see that it will make sense. So we start down here at a value which is less than A. As we move through time, we approach A, and eventually, as we approach infinity, we will actually be on this line here, line y equals A. Okay, but the reason why we don't draw it exactly, it's an asymptote. The reason why we draw it an asymptote is because we don't know the point at which we actually meet A. We just know that at A we will be on A, but as we move to the left of A, we don't actually know the point where we meet A. Yes, we have to draw it as an asymptote. Likewise, let's look at here. So between B and A, hopefully you can see that we started at a point which is close to B. Start here somewhere. And then essentially what we do is we move towards A. Okay, but again, we don't know exactly where it meets. It's rubbishly drawn, Alex. Okay, so we come down here and we meet the line, and it's again an asymptote to that point there. Poor drawing, I know, but hopefully you get the idea. Okay, so we started a value which is close to B, and as we move as we move forward through time, is that right? Yeah. Another way of thinking about it is that at this point in time after A, hopefully that makes sense, okay? I can keep explaining things, but I'm worried that if I keep explaining things, I'm going to make you more confused. So let's start here now. At this point in time, we start at a value which is close to B, and then we move towards C as we move through time. So we get there, and likewise here, as we move through time, we move towards C. Does that make sense? Hopefully it does. Okay, so as we move through time, essentially what we're doing is we're moving, we're moving to C. Okay, and these are no longer dotted lines, these are actual lines. Oh, don't do that. These are actual lines. Alright, so what is actually going on? So this is an equilibrium. Okay, and now we need to talk about this thing called stability. Now, stability is kind of a really simple idea. There's different types of stability. There's three types. There's stable, and there's two types of stable. I'll go into those in a minute. And there's unstable. That's kind of fairly straightforward. And if you look at our graph up here, hopefully you can see that because we move away from this equilibrium point, we call that B. So B here. So look at B. All the points move away, the arrows move away from this B, so therefore we call B unstable. It's a bit like, you don't want to go near somebody you don't like. You want to move away from them. Everybody kind of moves away from them. They're unstable. All right? But then stability is when you actually move towards the point from both sides. It's got to be from both sides, because I'll draw what's going on anyway. So two types of stability. So it's stable. So you've got unstable and unstable. And then two types of stable case. You've got this thing called Lyapunov, or Lyapunov, if you want to be Russian about it. Lyapunov and asymptotically stable. Asymptotically stable. All right, and the case sort of for each one. Well, clearly you can see that A is asymptotically stable because you kind of approach A from both sides, but those are asymptotes. And we talked about why they've got to be asymptotes, because you don't know when they're actually going to meet A. So you're just going to get closer and closer and closer, but you're not sure whether it'll actually meet A until you consider the other case. But even then, you're not sure where it's going to happen. So you're going to get asymptotes both sides, but it's stable, so it's asymptotically stable. Same with C up here. But then unstable, hopefully you can see that we move away from B. So you move away from B as we move through time. All right, and so that would be unstable. Now Lyapunov stable. Lyapunov stable. The easiest way to kind of explain this is that a Lyapunov stability, so asymptotically stable, hopefully you can visualise what that is. Lyapunov, basically, you've got this situation, you've got an equilibrium point in the middle, and you move towards the equilibrium point, and then you go past to some value, all right? But then you come back, and then you bounce. So essentially what you're doing is just bouncing each way, okay? So call this distance, these two distances epsilon. Maybe I should draw my equilibrium point over here somewhere so it looks a bit more equal. But yeah, what a Lyapunov stable basically is that we are close to the equilibrium point. We never actually go there. We keep missing. But because we're so close to the equilibrium point, you know, this is a really small distance. We're so close to the equilibrium point that we just say, oh, just call it stable. Yeah? Because we're bouncing. We never actually stop at the equilibrium point. But because we're going left and right all the time, left and right, left and right, left and right, left and right. Because we're going left and right all the time, but we're so close to our equilibrium point anyway, we just say, oh, just call it stability. Because we're bounded by these two regions here. Yeah, bounded by these two regions here. So that's Lyapunov stable. Asymptotically stable is where it kind of comes in from both sides. Okay, Lyapunov stable is where we're kind of going up and down all the time, but we're bounded in two regions. And unstable is basically where we move away from our equilibrium point. Okay, so hopefully that makes a little bit of sense. If you want to kind of have just a visualization of what stability actually means, imagine having a pendulum. Okay, so we start a pendulum on a table, and we've got a pendulum up here. And one case we start it up here, and in one case we start it, down here. Okay, and then we push it forwards. So we push it forwards. Now hopefully you can see that in this case, we're going to swing round over to here, and then we're going to swing back, and then we're basically going to get into a cycle here. But the point is that we start over here, and we basically get pushed to another equilibrium point. So it doesn't start and stop here. All right. But in this case, if we push it, hopefully you can see that we're going to end up over here, and basically we're just going to swing between the two. So, and eventually, because of dampening, this is going to end up back at our equilibrium point. All right. So, in other words, if we consider this, it's going to have the same thing now as the right-hand side, but it's going to start at a different equilibrium point to where we started. But here, it's going to start and finish at the same point. So we call this stable, and this unstable because it finished at different points. It's kind of different to where we started. All right, I think that's pretty much all I want to talk about stability and instability. So we've got three types of stable. This is just what you have to consider. You've got stable and unstable, and then two types of stable. So Lyapunov and asymptotically. Most of the time it's asymptotic. It's just in a few occasions it is actually a Lyapunov.